So welcome to this week's Origins Colloquium. It's a great pleasure to have Oksana give the talk this week. Hook is a professor in KU Leuven. He did his PhD at University of Liège. I think in '05 or '06 you finished up there. Then,
05.
uh-huh. And then had postdoc positions, Liège and also Amsterdam. Was in ESO as an instrument scientist for UVES, an ESO fellow. Was an ESA scientist at Space Telescope Science Institute in Baltimore, before then joining faculty at KU Leuven. There he runs a big group with lots of students and postdocs working on massive stars and massive star formation. And we're going to hear about some of the latest work today. So welcome, Hope.
Well, thank you. Thanks, everyone. So it's my pleasure to be here today to try to do something a bit different than what I'm doing. Usually, I'm measuring the properties of stars to study their evolution, but we've realized probably 10 years ago that we can use the same properties actually to try to say something about the way the massive stars are forming, which is and remain a big problem in astrophysics. So today I will basically present a summary of some of what I think is the key results from the group over the last few years. But let me first start by giving you a quick recap of what a massive star is, just in case people may not have yeah, people working on lower mass stars maybe or extragalactic topics may need a recap. So a massive star is a star that is born with a mass of at least 8 solar masses. And it's not so much about the mass that it matters, but it's about what it does to the star, is that those stars born with 8 solar masses are actually massive enough to end their life as core collapse, either as forming neutron stars and most likely a supernovae, or collapsing directly into a black hole. So observationally, because that's my job, there are the hot and luminous corner, left-hand corner in the Escher-Merschel diagram. They will stay on the mean sequence in that region for about 5 to 15 million years, and then evolve either at red supergiants or luminous blue variable. Some of them will become Wolf-Rayet stars too. The important parameters of those stars is, of course, the initial mass, but because of the strong luminosity, they may develop strong winds. There are strong ionizing radiation. So that's why they're important for galaxy people. And so that's basically the main reason why we study them, not only because we want to understand every stars, but because those are really some of the most energetic building blocks of galaxies. They drive galaxy evolution. They drive their nucleosynthesis enrichment, so carbon and oxygen. A lot of those material are produced in massive stars. And of course, nowadays, we're excited to study them and to study their end-of-life product through supernovae and through gravitational waves. What people need to realize is that the textbook evolution of a massive star looks more like this one than the one that you would find in the internet. Is that most of those stars actually are found in binary systems, as I will show. And that fact that they are in closed binary systems means that they will interact with one another. So the stars will not live their life isolated, but they will exchange mass, angular momentum with a companion. And that has radical differences in the way they evolve, but also that's a critical way to be able to form actually two neutron stars or two black holes that are close enough so that they can merge within a Hubble timescale. And we know that this is happening, and these binary interaction mechanisms are actually very good ways to produce the two initial compact objects that you need. But what I'm not going to do today is to study all this very interesting evolutionary sequence, but what I'm going to try to do is to focus on this region, trying to measure and characterize the outcome of the massive star formation, so that providing constraint that can then be used to try to see how those stars are formed. Right, so this is a picture from the review of Offner rates that you're probably familiar with. So those are different types of massive star formation and pairing mechanism to produce multiple objects. at different length scales, right? You have filament fragmentation, core fragmentation, let's scale of the order of a fraction of a parsec. You have the disk fragmentation, that is a less length scale of the order of maybe 10 to several hundreds of AU. And you have potentially captured dynamical processes on a slightly longer time scale. When the cluster collapse, for example, it's a very good moment to capture, but then you will also produce quite large binaries. What's interesting in this is that you see that the most compact, well, the mechanism that is leading to the most compact pairs is disk fragmentation, but that, according to textbook mechanism, right, you end up with the tightest pair of the order of 10 AU, and that's a number that I want you to remember because we'll come back to that later. Right, I cannot go to the next slide.
Can you say where that 10 AU comes from? I mean, I know the instability is mainly in the outer disk, but or I guess you'll come to it later. But what is the textbook for 10 AU there?
I am not quite sure actually. I think that it's gonna be harder to. The disk is too. I mean, if you are too close, potentially the disk is gonna be photoevaporated, right? So this fermentation needs to be produce pairs that corresponds to the size of the disk, and inside the inner rim, then there is no disk, so you cannot. From the textbook version, produce companions from this fermentation within the sublimation radius.
Mm-hmm. Okay, well, we can come back to it in the discussion. Yeah.
Don't hesitate to correct me because it's not my core business, this disks, but that was at least my understanding. What is more my core business is this. This is the observational parade grounds. This is on the horizontal axis orbital periods, right? I mean, or separation between component. And because you need to cover 4 to 5 orders of magnitude, you cannot do that with a single technique. And to be able to say something, you need to combine different techniques. The shortest period can be detected by eclipsing, as eclipsing binary, so by photometry, where you do see one star blocking the light of the other. Through spectroscopy or at wider separation, you need to require either astrometry. Gaia will be a game changer in that respect, but that is for next year. And then we've been doing a lot of study through interferometric binaries with the VLT interferometer in Chile. Let me first start with a study that started over 10 years ago, where we've been looking at the binary fraction of those massive stars through spectroscopy. And maybe that's one of my most well-known results, which is this data point. Took me 10 years of PhDs and postdoc work to get that measurement, showing that about 70% of the binaries were actually in a spectroscopic binary close enough to interact. And since then, what we've wanted to do is to check, okay, this is good. We have that in the Milky Way, but if you want to put that number for population synthesis of distant galaxies or for gravitational wave, we need to know whether this is metallicity dependent. We didn't know because we don't quite understand all the detail of massive star formation, so you cannot trust your models to decide whether the processes are metallicity dependent. So we organized 2 large programs at ESO, one in the Large Magellan Cloud, one in the Small Magellan Cloud, with metallicity of about half solar and a fifth or a seventh of solar, to perform the exact same measurement of sample of stars of about several hundred massive stars. And what we found, that was just published last year, is that it's maybe there are small differences, but on average, you see that we cannot fit a trend that is positive or negative in a statistically significant way. So we adopt the fact that it's more or less constant with metallicity. This is very different. Oh, so this was for the O stars. I don't know, there's been a problem with this, but the orange anyway is for the B stars. The B stars are stars that are 5 to 15 solar masses, the O stars 15 to 50 solar masses. So this is just a general result that metallicity doesn't seem to have a large impact. What I
Can
wanted
you
to show
just
you.
explain again, sorry, Hoopke, intrinsic binary fraction, then is it as simple as it sounds, or what
It is
does
as simple as it sounds. So we do observations. We measure radial velocity, so basically the Doppler shift due to the wobbling of the star. We apply a correction due to the fact that you have some limitation in detecting the radial velocity of longer period versus shorter period. This is just the Kepler law, so this is something
Yeah.
that we are
But
confident we can.
you're sensitive down to some mass of secondary, I guess.
Yeah, so we sensitive down to about masses that are 10 times smaller than the primary mass,
Uh-huh.
and we are sensitive to period up to 10 years.
And what sets the error bar then? For example, the Milky Way error bar is bigger than the LMC. Is it Poisson or is it something else?
Yes, so the error bars in the Milky Way, this is Poisson. LMC, we had a larger sample, so that's why we had smaller errors. Otherwise, the method is fairly similar, actually, so you
Okay,
can really compare those.
great.
I wanted to just put that in the context of the lower mass stars, where clearly in the lower mass stars, you tend to have indication that the process is metallicity dependent. What you need to remember is, I've been talking about the binary fraction, of course, but we do not see the same type of binaries. I'll come to that in a minute, right? The most massive stars tend to be in shorter period than the lower mass stars. So that's another difference that we see in the massive star formation process. All right, so this, if you just look at metallicity, right? So here we only have 2 data points, but Offner in the same review, right, has been slicing the mass axis into many, many more bins and showed I mean, this is something that's been shown earlier, right? I'm citing Offner because that's the most recent review, but we have a very nice increasing trend as a function of metallicity, with about half of the solar type stars being in binaries, but almost 100% of the O type stars being in binaries. The difference between this result, 70%, and that result, like 95% or 100%, is the fact that in the previous image, we stopped a period of 10 years. And in this diagram, you are allowed to go to much larger periods that add another 20%. What's also interesting is the dotted points. Those dotted points, they are also increasing, following a similar trend, but this is not this time the multiplicity fraction, is the number of companion on average. And you would see that a solar type star will have on average 1 companion, but massive stars will have on average 2.5 companions, which is basically telling us that the most likely outcome of the star formation or the pairing mechanism for massive stars is actually a triple system, not a binary system. There's something we did more recently, is that we went back and checked about this nice curvature that you have here, and we were wondering whether this was real, because based on our observer experience, there's actually more biases in this region than in that region. So we perform, it's a very colorful plot, but what's important is to realize that we combine photometry, spectroscopy, and interferometry on a sample of B-type stars, so 5 to 10 solar masses on average. And what we found is that, whenever you combine all those techniques, you're actually boosting the true binary fraction up to almost 100%, and you're reaching a number of companion that is very, very similar to that of the most massive stars. So it seems that at least above 5 solar masses, every star should be in a binary or a triple system, and that it has a number of companions around it. So that's the most likely outcome of OB star formation, and that's maybe my takeaway message number 1, is that the end product of massive star formation is a triple system. So that's about the number of companions that you make, but there's also a question about what type of companions, right? You already asked a question about what is the mass ratio of those companions. And so this is a diagram that, that we have. What would be the relation if you would plot the cumulative distribution, a function of period and of mass ratio? And typically, what has been the takeaway message is that if you take uniform distribution, uniform in mass ratio starting at 0.1 and uniform in the logarithm of the period, you're actually quite close to reality. So if you don't want to have complicated, or if you want to just adopt a simple model, take this. The next slide shows a lot of measurements, right? Oops. Ah, yeah, no, so yeah, I will show in a minute way more measurements. But I think that if you just need to remember something, this is those simple relations. So of course the question is, that's the simple picture, but can we see that there are differences with masses range, with metallicity, with the environment, with the age, for example? And that is what I do in this plot. On the left-hand side is only a period distribution measured for O-type stars, for B-type stars, in denser cluster, in the Milky Way, in the large and small Magellan Cloud, in much less dense OB association, and you see that there are very, very few differences. And that if you do a full analysis, you can always find a period distribution with an index that is more or less, that is close to zero, which is this zero value means the flat period distribution. We've done that for the period. We've also done that for the mass ratio. We don't have such a nice picture because a lot of that is hidden in the bias correction. But clearly, each time we have tried to measure it properly, we came up with a flat mass ratio. So no strong difference with metallicity, no strong difference with different mass range, the B stars, the O stars, no strong difference with the density of the region in which we've been studying those populations. So that's the takeaway message number 2, that the log period and the mass ratio distribution are more or less uniform and they're not strongly impacted by the local environment. There again, we are limited to object with a period of 10 years because that has been done with spectroscopy.
When you say local environment, perhaps I could just ask, when you say local environment,
the density. So whether it's in a cluster, whether it's in an OB association, whether it's in Milky Way, whether it's the in the Magellan Cloud, so a different metallicity. Yeah.
Surely runaway stars are different, aren't they? Would you say, or?
The runaway stars are different, but in our understanding, the vast majority of the runaways have been produced by either dynamical encounter or by supernova explosion in the binary system, so that they're not representative of the initial binary. It is 100% correct that if you take a sample of runaways, the binary fraction is much lower, if not very close to 0. Yes.
Okay. Well, we can come back to it in the discussion how the environment variables measured and so on. Okay. Yeah. Great.
All right. I've been telling you that the initial period, initial distribution is actually quite simple to understand, but it's actually not so simple if you think about it in terms of the scale of a forming massive star. And this is just an example of a recent, very beautiful measurement that's been done. If you scale that system that has been analyzed to the actual size of the binary separations, this is the kind of picture that you have, right? So is that almost all the binaries that I've been studying so far, they have a size which is about the same size or smaller than the observed disk that is accompanying the formation of a massive star. And that is something that we actually cannot or should not ignore. We've been ignoring it a lot, but what we measure is the current period distribution, the current mass ratio distribution cannot be, well, it's probably have been impacted by the fact that this has been forming in a disk that has been very potentially very dynamical and evolving on reasonably short time scales. So when we realized that, we decided, okay, our sample mostly are formed by stars that are 2 to 3 million years old, sometimes 5 million years old. Can we identify a sample that is as young as possible? And that's what we did here. It's M17, that's a cluster which is 1 million year old. And it was very difficult to obtain spectroscopy. So what we could do the first step was to take only one radial velocity, one spectrum per star, and to study what we call the cluster one-dimensional velocity dispersion. So this sigma 1D, right, is a combination of three different contributions. There is the error bars of your measurement, typically 1 or 2 kilometers per second. There is the intrinsic distribution of the stars within the cluster, as you all guys know. So this is probably of the order of also 1 to 2 kilometers per second. And then if you have some spectroscopic binaries that are orbiting, that will add a third component. So for the stars that would be in spectroscopic binaries, there will be a distribution. What we did is different simulations. If you have no short period binaries, what you expect to see is that this contribution is very small and the rest is dominated by the error bars and the clusters. And you should get something like this black histogram. If you have short period binaries, then those short period binaries, even if they are not two numbers, they would very quickly, this term will very quickly become dominant. And then you would observe something which is this very broad red histogram. The reason why it's very broad is that it really depends on when in the orbit you're observing the system. And so there is a wide variety because you only have one epoch per system. So what we actually observed in M17 is this black value here. So the observed distribution is the order of 5 kilometers per second. And this is directly telling us that there is no short period binaries in this system. So the only population for which you can measure binaries that are of the order of 1 million year old, what you do find actually is that there is no short period binaries. Of course, you can say, oh, but that's because there's no binaries at all. But that would be strange because we do know that there's a lot of massive stars that are formed in binaries.
Is this only B stars and these are only massive stars, is it? Or
That's only O stars.
only O stars? And how many O stars are here then?
I think in that sample, we had 12.
Mm-hmm.
So it's not a large sample because the cluster is only so massive that there is so many massive stars. But the result was so stringent that it's actually very significant from a statistical point of view. What we did do is to try, okay, this is spectroscopy. You cannot detect stars, binaries that are shorter than 5 to 10 years. Yeah, sorry, binaries that are longer than 5 to 10 years. And then what if those binaries do exist, but they are at larger separation? And so we went for interferometry and we tried to measure those objects. Unfortunately, we could only observe 6 of them because of bad weather. But for every single of the one that we observed, we showed that it was either a binary or a triple system. So this cluster is full of binaries and triple. They just at a wider separation than expected from when compared to all the cluster. And that was an idea by Maria Ramirez-Tanus. What she did is she looked at different clusters with different ages. And as you may know, measuring the age of a young cluster is not so easy. So there are significant errors on the age direction. But if you just compute this one-dimensional velocity dispersion along those clusters, and you plot that as a function of the age, then there is a trend that seems to be statistically significant, right? And so the suggestion that here we have this M17 cluster that contains wide binaries, but we have also much older cluster, and this one I know it very well because I studied for my thesis. There are 11 short period spectroscopic binaries in a sample of 16, for example. So the suggestion or the evidence that we think is starting to emerge is that there is a migration, a hardening over a time scale that corresponds to a few million years. And so that's my takeaway message number 3. All right. Let's have a look at what's happening at larger separation, because at the moment I've been focusing on those systems that have a separation of less than maybe 1 AU. But if we want to look at a wider separation, there's also a lot of interesting results. So this is a study, a survey we did with interferometry. We did the observational part 10 years ago, but it's only much more recently that we have been able, or we put the effort to translate all those observational diagnostic that we had into physical units, mass ratio and separation. And you see that this region is also full of binaries. So we have binaries here that I don't show, and in that region, we detect a lot of new binaries. But then you can see that, oh, okay, sorry, above this line, right, we are more or less complete because we have the detection curve of our instrument here in color, and we are almost always above this curve. So there is almost no observational biases, and it seems that around 1000 AU, something is happening because we start to lack the more massive companion in that region. And we can do a full analysis that's been done by a postdoc that was here a couple of years ago, Frank Tremper. And what he finds is that in those bright companions with magnitude difference less than 4 magnitudes, that correspond basically to mass ratio of 0.1, 0.2, the mass ratio distribution is much steeper. So we have many more low mass companion at large separation than at close separation. And the trend is compatible with what you see at spectroscopy, where in very short separation, you have a flat mass ratio distribution, and then you start to steepen the mass ratio distribution. What's interesting is if you don't focus on the bright companion, but you take everything, then suddenly the mass ratio, the companion mass distribution is 100% compatible with salpeter because salpeter is here, the green line. So clearly we have different type of companion and we need to have different pairing mechanism to produce all those companions. Maybe what's in terms of orders of magnitude, what's important is to remember is that the mass ratio distribution is period dependent. That's not the first claim that the first time it's been claimed, but we find the transition at a very different, much wider period than what's been claimed before. And our length scale is about 500 to 1000. If I have a few more minutes, I've been saying that there's a lot of triple systems. Those triples are reasonably wide. So we're talking about orbital period of 5 to 50 years. But because we've been continuously monitoring those systems, we are now able to provide three-dimensional orbit for many of those systems, which means that we are able to study the properties of the inner and outer binaries in comparison to one another, but also to look at how is the total mass distributed between the primary, secondary, and third star in the system. So in our sample, we had a initial sample of about 100 objects, 120 objects. Half of them were detected as multiple in the interferometry region, and 27 of them we could identify them as hierarchical triple. Those are reasonably tight triple, right? We know that they are triple with much wider and much lower mass companion, but here we're talking about triples that have 3 massive companion within 300 AU. So that's the kind of triple that we're looking at, right? So we're not looking at trapezium-like triples. Those occurs, but they are much less frequent. And we're not looking at hierarchical triple where we have an inner binary, a third companion, and then an even further away fourth companion. We are in this configuration. So that has been studied by Emma Bourdier, former PhD student, and the paper is now accepted. So if you plot the inner separation versus the outer separation, what you will see is that the vast majority of those systems have a large ratio between the inner and outer separation, which means that the semi-major axis of the outer companion is much, much larger than the semi-major axis of the inner companion. This is what you expect from stability criteria, but you will see that those stability criteria tend to predict a mass ratio between stability criteria where the outer system is about 3 to 10 times larger than the inner systems. But what we see is that we are much further away. So there's very few systems that are close to the stability criteria. So either the stability criteria have been underestimated, they've been too strict, or nature doesn't form stars in that region for some reason. What's also interesting is that is to look at the distribution of the masses, then it's much less clear. While we have a clear regime of hierarchy in the separation, in the masses, it's not the case. Sometimes so the primary is by definition always the most massive stars, but sometimes the second companion is more massive than the third companion. Sometimes the third companion is more massive than the second companion. Sometimes, yeah, so this is what this complicated plot is showing. Right, so that's my fifth message, and I have a final one. So tight multiples are dominated by hierarchical triples, but there's a very diverse hierarchy in the masses. There's one thing that we have not been able to do so far is to look at the relative inclination of the inner and outer binaries, because of course that's what you want to do if you want to study the Kozai-Lidov mechanism or see the impact. And the reason is that you need the full orbit of the outer companion to do that. This is coming, but it's just taking time because those orbits have periods of 10 to 50 years. And so it takes a bit of time to get the observation. The last thing we did is that a current PhD student is Jasmine Rankin. The slides that she presented actually this morning in her PhD progress presentation meeting. What she's been doing is you look at eclipsing binaries. So if you look at eclipsing binaries, you are necessarily at a much tighter regime than what's presented here in this disfragmentation diagram. We are well within 1 AU because at larger separation, the chance of alignment are becoming small, and so you don't have eclipses. But even if we don't have a lot of chance alignment, we've been using tests and a catalog that has been published by a former PhD student from Coney Arts. And that person had identify 17,000 eclipsing binaries with masses between 1 and 50 solar masses. And what we try to do is simply to measure the intrinsic period distribution in different mass bins that are represented here. We do that by combining photometry, distances, and then the information about the period. There's an entire Bayesian framework that is behind that I'm just not going to explain. I just want to give you the result. If you slice your period distribution in different mass bin, this is what you obtain, with the darkest green being the most massive one and the darkest brown being the least massive one. If we just plot the orbital period, it's a bit messy, but what you can do is to plot the distribution of scale radii. So you take the primary radius divided by the separation of the binary, because a low mass stars being much more compact can simply have tighter binaries than a higher mass star. That's the scaling that we choose to adopt. So those distributions are fully corrected. Those are not the observed distribution. This is bias corrected. And what we were hoping to identify is that we would have been hoping to identify the fact that the low mass stars at a certain type of period distribution and the highest mass stars would have a completely different one, and we should be able to see a break at a certain mass length or mass value, right? But this is not the case. There is a very smooth transition from the 1 solar mass stars to the 15 solar mass stars, simply that they are proportionally more and more compact because you can fit 2 stars in a, I mean, the stars have a smaller radii. I think basically this is what it means. What's interesting is that if you look at the B-star prediction, the model of Tokovinin and Mu, that was a bit of an ad hoc model, but they were combining discrimination and migration. We are more or less in the same ballpark order of magnitude. So this is a potential indication that for detailed prediction and detailed simulation, combination of discrimination and migration is potentially the way to go, need to be checked. But this is then would be telling basically the same story as the one-dimensional velocity dispersion that I was mentioning earlier. So that's my last message, right, is that at shorter period, we have no mass-dependent break in the period distribution. So we cannot say, here, the massive stars and the low mass stars are actually forming through different channels. That was a bit the idea a few years ago. But maybe there's simply a scale-up version with some minor adaptation that would be able to explain both lower mass and higher mass binary formation. There's one caveat. This beautiful result that took a lot of work is only limited to period of 10 days because that is what tests can do. So we are now working in going to much wider binaries because there's a lot of binaries that have wider separation than 10 days, of course. Voila, I'm fully aware that there's a lot of different results and there's a lot of food for thought. So I'm not expecting that you pick up on everything, but I wanted to throw as many messages as possible. Those are observational results that need interpretation. And I'm happy to discuss that with you now and of course later if we find things that we want to dig further together.
Great. Thank you very much, Hook. That's great. We have plenty of time for questions and discussion. You probably want to keep your slides on the screen so we can jump to different parts. Maybe we can structure the discussion along the following lines. So there's basically the frequency of binaries and multiples. There's the masses, and then there's the orbital properties. So let's start with the the frequency of binary systems and so on. The metallicity result then, so I guess this is, I'm learning here. So in low metallicity systems, multiplicity is definitely rising for low mass stars.
Yes.
That I guess, is there an explanation for that?
I think this is the co-fragmentation that is the cooling mechanism is metallicity dependent. And it's high, yes.
Yeah, well, cooling would be weaker when in lower metallicity, but the binary fraction is rising. If you could just show the data again that illustrates this.
Oops, sorry, this one. Yes.
Yeah. So that's anyway. It's can you comment on the measurements that people did for the low mass points here? I'm trying to remember which studies are these then?
Those I think it's mostly Max Moo that did that of solar type stars in the Milky Way. So those are all Milky Way measurements. It's just that at different places in the Milky Way you can probe different metallicity environment. So it's not the same for the massive stars. The massive stars, because they don't live very long, you need to go to other galaxies to probe the different metallicity environment. Here, if you go to the, for example, you can go to a higher metallicity. I need to go back to the paper, but I'm pretty sure it was the cooling mechanism. But I agree with you that in the simple term, it should have been that the cooling is harder, so it's harder to make binaries.
But so that I mean, I'll have to also look at this paper, but it's they've got a measurement of 0.1 solar metallicity. That must be an old dwarf, is it, or something? But so I'm curious which environment that is, and then. Can the low mass systems be done in the LMC and the SMC?
No. This is Milky Way. I'm almost 100% positive. Yes.
Well, we have a region we like in the outer galaxy S284 that's about 1/3 solar. So maybe somehow we should think how to do it there. Okay. Any other questions related to frequency that can include environment? I mean, you mentioned this business of there's no evidence for short periods early on, but then so then they're evolving through some kind of processes, migration or something. But that you might expect would have an environmental dependence. You know, in a denser region, you have more chance of interaction and hardening. So what's the story there?
So you are 100% right. So this hardening time scale is a bit ad hoc. I mean, it's not ad hoc. It's like if you want this slope that you have has a certain basically hardening time scale. What I personally think is that the cluster environment is not so important. It's possible that the dynamical interaction that leads to the hardening, because I mean, you need a dynamical interaction to make hardening, right? I'm not learning you anything. May happen maybe within either the disk or within the initial companions of the massive star, right? So you would have maybe a small cluster of I don't know, maybe 3, 5, 4, 6 stars that are within this region of maybe smaller than 10 AU, and then the hardening is happening in that region.
You're saying the
But
massive star would have its own local environment, but
yes,
so it would be born with enough stars within the same system to then do the
yes.
dynamical rearrangement.
But as I say, it's I'm not a specialist. This would need to be tested. That would be a way simply to get rid of the local dependency of the cluster, right? The challenge is that we could do that measurement only for one cluster, so we don't know how many very young cluster with different environments. It's yeah, because those clusters less than 1 million years, they tend to be very redundant, and the observations are simply difficult.
Mhm. So Ayush, help me, and Virginia, side for other questions. Any other questions for Hook on this kind of topic here of
I have
multiplicity?
one question for the later part.
Let me just ask then, the triple fraction in M17 is the higher order fraction is the same as it in M17 as
Yes, so that was this. So we get, so as I said, it's only 6. So it's not a large sample, but 3 of them were binaries, clearly identified, and 3 of them were triples.
Mhm. Okay, very curious.
We
Ayush, why don't you go?
asked for more time, but we never got the more time, so it's a bit of
Yeah,
a shame. But
we can keep trying. Ayush, why don't you go ahead and ask your question?
Thanks for the nice talk. My question was when you were showing the hierarchical multiples later, are those systems formed that way, or they are you have like a group of some of them are hierarchical, some of them are non-hierarchical, and by the time you observe them, you only find the hierarchical ones because they are like surviving this process.
that's possible, yes. I mean, we never see the zero age truly, right? The stars that emerge from the cluster and becomes optically bright or infrared bright only about 500,000 years to 1 million years after the true formation. So yes.
Any other questions online or here? Raise your hands. So we can go maybe to the masses. You mentioned that let's say I'm drawing a multiple system. So the secondary is consistent with a salpeter mass function drawn from below the primary. Did I hear that?
It really depends on which separation you are looking at. If you are looking at shorter binaries, then it's definitely not salpeter. Oops, where is this? So here is, for example, the distribution of separation between 1 AU and 100 AU. Distribution of mass ratio for binaries with separation between 1 and 100. And this is, yeah, minus 1.2, while salpeter should be minus 1.6, right? Minus 2.4. The thing is that at wide separation, where was my picture? There, in that region, there are actually so many stars that those statistics are becoming, well, they don't matter so much. And so those stars at wide separation, if you do a statistics where you don't apply any mass ratio cut, will dominate. If you don't make any cut, then indeed it's salpeter, 100% true. The problem is that those show the separation, we just don't have the observational technique to see whether those stars exist.
But you can fit if you fit a power law in the region you do observe, and you're saying that's definitely more top heavy than salpeter, is it, in the inner region?
There, yes. Yeah, I mean, you see the difference, right? Here it's definitely salpeter, and
Yeah.
there it's, I mean, you see by eye that this is more or less flat along the vertical axis.
Well, that relates. I mean, there was a number of years ago this claim that equal mass is more common than you'd expect. So I guess it's sort of similar.
Yes, but that claim was that equal mass was really stars that had a mass difference of 5%, so like a mass ratio above 0.95, and that we don't quite see. We see things that are in the same order of magnitude, but not really mass ratio that are close to unity. I mean, there are some, but very few, so there's no excess in that region. What I think happened for that specific study that made that claim is that they were looking at eclipsing binaries, and the sample was biased to stars that actually started to interact and exchange mass, and that actually tend to equalize the mass ratio. So they were right. There is an excess of equal mass binaries, but because of stellar evolution, not because of star formation.
Right. Well, the mechanism they proposed was this, disk fragmentation, and then the secondary is the one that accretes always, and that would equalize the masses, right?
I'm aware of the mechanism they proposed, but I don't believe it.
Yeah. Well, but there is the closest separations there are pretty close to one. So
here,
yeah, I mean you have several.
It's 1 AU, right? There is another regime. The eclipsing binaries would be a 0.1 AU. So this diagram is missing another order. There's one order of magnitude here which is missing, which is actually full of short period binaries.
Okay, any other questions on the masses? Then let's see. So then if I'm drawing the semi-major axis of the orbits, now what I vaguely remember is when you showed it was fairly flat in log p, but isn't that there's the typical separation is about 30 AU is what I remember with a broad peak. Is that, and you're saying that doesn't depend on mass of the primary? Or
so for the massive stars, it seems not. No, we have the same results for a sample of stars that is 10 solar mass and a sample of stars that is 30 solar mass.
And is that there is this sort of broad peak? Is there a peak at 30 AU?
No,
is there a characteristic scale, or is that gone away?
It's gone. Do I have a good plot for that? I'm not sure I have a good plot. So those are the observed period distribution. It's not bias corrected. If you bias correct them, you will increase the number of wider separation system because they are more difficult to detect, and you end up with something which is fairly flat. This is different than the, I don't know, solar type stars that will have a log normal period distribution. We don't see that for the massive stars.
So there is a difference. So the low mass stars do have this characteristic. I mean, 30 AU is what I remember, and then
yes.
So for some reason there's a more frequency to have your secondary at that orbit, but it's broad peak. But you're saying high mass is just flat.
I must say, I have somewhere public outreach figure that shows the difference. Yes.
Mm-hmm. Well, I guess the mass where that transitions would be interesting to know then.
But this is exactly what we were hoping to find where we did this study, right? Where we try to plot the period distribution of solar type stars here and massive stars there. But the transmission is smooth. Of course, it's a study that is limited to a period of 10 days. And that's a big shortcoming, but this is the data that allowed us to do that. But yes, that was the idea. Solar type stars have a log normal distribution with a very wide separation. Massive stars have a flat distribution with a typical separation of the order of a fraction of an AU. Somewhere in between a 1 solar mass star and a 10 solar mass star, things need to change.
Mm-hmm.
Yes. So Gaia will give us the data we need to do this. So oops, where's the plot, right? So we have been using eclipsing binaries. We were in that box. Gaia, they are full. So in December 2026, will give us the data we need to repeat the same experiment.
Okay. Well, maybe we can come back to the environment question. And you're mainly looking at O and B stars. So they are in associations generally, or what fraction of your sample are in bound clusters versus unbound associations? Just so I get a sense of
So I would say it's about half about open clusters, and about half in open clusters and the other half in associations.
mhm. And the runaways we mentioned are not. I thought it's like 5-10% of O stars are runaways anyway. Are they a
Yes.
separate group?
So if we look at the runaways, we have so basically when we did this survey, we include all the yellow stars, but we have removed the runaways from the final statistics because we know that the initial statistics have been destroyed. So there the binary fraction was only 15%.
Right. Okay. Mm-hmm.
So it's the runaways have been dynamically processed, well, either through a kick through a supernova, right, or through a dynamical encounter, and that tends to destroy
Mm-hmm.
the binary.
Mm-hmm.
Yes.
So how many bound clusters are we talking about that are would contain are in your sample?
It's about the same as those ones, so it's about 6, 4, 5, 6.
Mm-hmm.
Yes.
Right.
The problem is that every of those clusters only have 5 to 15 massive stars, so it's very difficult to try to split the sample, right? And so we try to correlate that the same way we did it with DH. There seems to have a correlation. If we try to do that with density, for example, the local stellar density in the clusters, there is nothing clear that come out. So the age trend seems to be more important than the density trend.
Mm-hmm.
But I mean, we clearly, I mean, R136, for example, is a known quite dense cluster, right? There we have the same binary fraction as elsewhere.
Mm-hmm. So what are the prospects for getting this sample bigger here? This seems to be limiting things.
So there are several large spectroscopic surveys like SDSS, like the WEAVE and Foremost, that are collecting hundreds of spectra of dozens of stars. So I think that's the next big things. Many of those surveys just started. SDSS is finishing, but the quality of the data in SDSS is not so amazing. So for the massive stars, there's a lot of interesting things in SDSS, but for the massive stars, it's a bit limited. So Foremost, I think, and Weaves are the two new, surveys that will deliver data within the next 5 years. I think we will have a much better
Mm.
view. Yes.
Great. Well, we're near the top of the hour here. Any last questions for Hook? The ELT is coming, and any comment on what we can interferometry with the ELT? Is what's the plan, or is something going to happen that's going to improve things here?
Well, the ELT where is, do I have a plot? The ELT is a 40 meter telescope, right? With it will not have this, it will have basically a resolution power that will be able to detect objects that have a separation of I don't know, 20, 30 milliarcs again. Interferometry will remain more sensitive because interferometry is limited by the separation of the telescope. And at the moment, with Chara, for example, we have a 300-meter separation. So the interferometry is the equivalent of a 300-meter telescope, but it's not as sensitive because the collecting area is smaller. So it's a bit, you need to play with both advantages. I think what the ELT will allow us to do is to try to explore lower metallicity environment in much more distant galaxies.
Mm. Great. Any last questions for Hook here? Yes, Asatan.
Hi. Hi, thank you for this talk. Can you show a picture about this mass ratio?
But
Yeah.
is it those ones that you
This
want?
one, no, this one, yes. Thank you. Do you know it is age clusters? Because I'm thinking that maybe here when star formation is going, it is very stars binary. Maybe I don't know. And after it is lost, it is some binary stars lost and will evolve a single it is single stars. And here is we see that after 1000 AO,
Yep.
this mass ratio it is low than it is 0.15. Yes, it is. Do you know it is age clusters, and maybe it is show us some evolution of uh, our star clusters, evolution of binary stars, maybe. Sorry if it is saying something incorrect. Yeah, thank
No,
you.
no, I think this is a good idea. I don't think we have done that in that specific diagram. What we've looked is the evolution of stars, because some of the stars are younger, some of the stars are older, and we know that because they are dwarf and giants, and some of them are supergiants. And when we tried to do that exercise, there were no obvious trend, but we did not slice this diagram per cluster, at least not that I remember. So
Mhm.
that's something we could do, I think, fairly easily because we have the cluster membership in the database.
Yeah, it is maybe it is at somewhere it is age clusters and with color, maybe color bar. Yeah,
Yep.
Yeah, we should
Thank
definitely look for evolutionary effects with environment as well. I mean, they should happen. So, okay, we're at the hour here, so let's thank Hook again for a great talk and discussion.